Welcome to the fifth lecture of the Geodesy track in the Advanced Techniques for Mobile Sensing and Robotics. Today we will talk about structure from motion, or how to get point clouds from images. So this is again the content of the whole lecture, and we are now in lecture 5, from images to point clouds. So far we talked a lot about mobile laser scanning. That means we discussed how we transformed a laser measurement, which is here done from the rotating laser on top of a vehicle, for example, how this measurement of a 3D point is projected and transformed, not projected, transformed to a global coordinate system, so that we have a globally consistent and georeference point cloud. So this was our main topic of the last lectures, and we talked a lot about how this measurement is generated, how we calibrate the sensor system, because we need to know all the internal orientations and transformations between the sensors and the actual vehicle. And we also talked about how the trajectory is estimated, which gives us the position and orientation in some global coordinate system. And finally, we get a point in that global coordinate system here. So this was what we've done so far. We called it mobile laser scanning. And today we talk about a different way of, let's call it mobile scanning or mobile mapping, which is based on images. So let's have a look what happens if the sensor that we're moving around is a camera and not a laser scanner. So we have this example here where we have a UAV, an unmanned aerial vehicle, which does some flight pattern, means it flies over some object, which is an agricultural field in this case, and takes many images from the air. And we use this to reconstruct a 3D representation of that agricultural field. So if we look at this equation, the georeferencing equation that we always used for the laser scanner, then we see that we have here in this case now some sort of 2D image coordinate, because our observation in an image is a 2D coordinate in the image coordinate system. And then we need some sort of transformation to go to a 3D world coordinate. And this is not possible. We cannot calculate a 3D position of an object from a single camera observation. So the question is what to do. And the answer is known as a process called structure from motion. Also, multi-view stereo is a word which is always used in that context, and I will go to the meaning of these words a bit later. So the idea is that if we have a 3D object here, and we can see single points in that object from different images, right? So we have an image taken from here, another one taken from here, another one from here, and so on. Then if we see these points from all these multiple images, then we can reconstruct the position of those points. So we can reconstruct the 3D model using the camera, a moving camera, and this is what's called structure from motion. There's a very strong, so this is probably not a surprise for you, because there's a strong link to what Cyril Dachnes told you in the first part of this course, right? So especially in the lecture Direct Linear Transform, Camera Calibration and Localization, that was the topic, right? The topic was the projection of something in the 3D world, in world coordinates, into the camera coordinates. So what happens on the way from the object to the actual observation that we do with the camera? This projection here from world coordinates, 3D world coordinates, to image coordinates. And these image coordinates are the actual observations that we have. And on the way there are many parameters that we need to know. And these are the 3 translations and 3 rotations of the camera, so that they are the so-called extrinsics of the camera, so where it is in the world and where it is looking to. And then The other thing are the so-called intrinsics. These are parameters which determine the behavior of the camera, of the lens system, and so on. And the other things are the object points here, which are projected to the image. So what we now want to do, we want to estimate the intrinsics and the extrinsics and the object points from multiple images. So this is what is usually done in this so-called structure from motion pipeline. This lecture will be not a detailed photogrammetric and mathematical background of this process, right? So it gives an overview about the different steps, about what happens and what are the results and so on, but it will not go in mathematical depth to explain the bundle adjustment and all these things. And it will also focus on UAV-based mapping. Yeah, so because this is what we usually, where we usually use these methods, and I will have some examples where we used UAVs to generate 3D point clouds of some environment. Okay, let's go to the definition from Wolfgang Försner's book to explain some words and some meanings of different processes. So in this book, this is basically the same equation that we've seen before, where we have a set of features in the image space, right? In the space of the image, in the 2D image space. And we these set of feature points in the image space show a set of features in the object space, which is called here the capital F, right? And this projection from this object space to the image space needs a set of orientations and a set of camera parameters. So these camera calibration parameters are the intrinsics from the slide before. These O here, the set of orientations, are the extrinsics, and these are the feature points, and this is a transformation. So the set of orientations, and it's a set because we have many of them at different times, it's called motion sometimes. And this set of features in the object space is called structure. Yeah. So this is where we can, where this naming structure from motion or even motion from structure comes from. Yeah. Okay. So now in the book there are some definitions on different estimation processes, and I listed them here because it's quite good to know the differences and to understand what is actually estimated here. So here we again have this function with a projection. And if we now try to get the orientation from the structure, yeah, then this is called motion from structure, or estimating the orientation. That means that we try to estimate the different external parameters of the camera from correspondences between image features and object features. Yeah. So and this is what's called orientation or motion from structure. Then there's something called calibration, which is usually meant to determine the intrinsics of the camera. This is usually done using image features and possibly given features in the object space. Then there's something called reconstruction or structure from motion, which has the goal to get the structure, meaning the feature points in the world coordinate system, from observations in the image space. Yeah? Then this is called structure from motion. So we want to reconstruct the 3D geometry of the environment. Another thing is called relative orientation. And relative orientation means we determine the relative pose between multiple images, and we also determine a local screen description, Fi. So this is basically, it's actually very similar, and this is done as part of later structure from motion pipeline. But the main point here is that it's relative, right? So we determine all the relative poses between the images, and we also determine a local scene representation or local structure from corresponding image points between from points which are visible in all these multiple images here. So we need corresponding image points here. Absolute orientation means to get the global scene points, the global object features, from a local object feature, which we might have derived here in this estimation, but then we want to have a global coordinate system, and then we need the so-called 3D control features. We will see that later in a figure. So if we go from a local description to a global description, we need some sort of known coordinates to do that. And this is called absolute orientation. And then there's something called bundle adjustment, which is basically deriving the structure, like the capital Fs, the orientation, and the camera calibration from these observations. So basically we have these observations, and we derive all of those here using a so-called bundle adjustment. If this Fi here is valid in a global coordinate system, known in a global coordinate system, we also need 3D control features or direct measurements of some points or poses, for example via GNSS. We can see straight away that this bundle adjustment here combines everything that we have done so far, so that we have seen on the slide before. And the other interesting thing to mention that this is very close related to SLAM. In a bundle adjustment, we basically estimating the same things as we do in a SLAM algorithm, which you also learned about in Cyril Stachner's part. So here we again see a figure of this of some images which have been taken from a drone or from a UAV, and from each of those is a camera, and each of those can see certain points on the ground, right? And the bundle adjustment is then estimating the position and orientation of all these cameras, the position and the position of all these points, yeah. And if there are also points with known coordinates, like this one here, these here are so-called 3D control features or control points. If we have them in a global coordinate system, then we can basically transform the whole system to a global coordinate system, and then we know also the camera positions in a global coordinate system. The other way around would be to know positions of the cameras here in a global coordinate system, and this is a different way of georeferencing. We will talk about that later as well. Okay, so these are the definitions from the book from Wolfgang Förstner, and I also want to say additionally that what most people actually mean today when they say structure for motion or the structure for motion pipeline is this bundle adjustment which is mentioned here. So it's the bundle adjustment here, including all necessary steps to create the initial solution, because this is a process which needs an initial solution, relative orientation, sequential adding images to create an image block, and all these things which I will explain quickly in the next slides. It's not necessarily scaled and in absolute coordinates, right? Structure for motion can also result in a 3D structure which is not on the correct scale and which is not having absolute coordinates. The result of this structure for motion is a sparse point cloud. Yeah, that's what it's called. So it's a set of these feature points in the object space, the image parameters, meaning the position orientation of the camera, and the camera calibration parameter. So what is a workflow of this structure from motion pipeline. I will go through this, and then in the next slides I will say a little bit more about the different steps. But first we start here. So the first part is when we get our images here, is to find features in the images and find all these matching points between the images. Yeah? This includes detecting the features and finding correspondences and so on. So this is to get relative orientations between the different images. And then there is the part which is called SFM, the structure for motion, which is this bundle adjustment that I've said before, which then estimates all these points and all the camera poses and estimates this using this bundle adjustment. In this part, there can also be the so-called georeferencing, which can be done by the position of the known position of the cameras or known position of ground control points, which are somewhere in the image. And then there's a third step, which is called multi-view stereo. Multi-view stereo means that I use this part, that I use the sparse point cloud and the images from all these cameras to create a very dense point cloud. And this dense point cloud is then the result of the whole pipeline. So I will now go through the different steps. So the first step is extracting features, right? So we extract features from the images and find very distinct points which we hope to find also in other images. Yeah, there are different names. I will not go at all into the methods how that works, but there are called features called sift or surf or brisk. They're finding these features can be corners or blobs. So there are different ways of finding distinct features in the image. The second step then is describing these features. So it's a feature description. That means I calculate for each of these features, I calculate a vector of numbers which describes the property of that feature. Yeah? So it can be gradients, intensities. There are different ways of coding the feature description. The reason to do that is that we can find features which we find in one image, we can find it in another image. And this is the whole goal for this step is we find features and we find the same features in other images, or we find corresponding features. This is the main thing. There will be many outliers, so this feature matching usually includes some outlier rejection mechanisms. But the output of this step here is a set of images, and for each image a set of features, and then correspondences between the images with respect to the features. The next part then would be that actual structure from motion part. Yeah. So there are many different algorithms how to do that, and I try to give a very rough idea what in general happens there without going into details. And I hope I'm not, by simplifying this so much, I hope I'm not doing an error. But my goal here would be that you understand the general idea behind it and not how the actual algorithm works. So we initialize usually using two images. Yeah. So with two images, you already can get, and of course the features and the correspondences between the features. You can already get the relative orientation between those images, and initialize the structure means have some points in the object space, which are basically the 3D representation of the features that have been found in the images. And then there are more and more new images added. One by one, new image is added. And for each image, this new image is then oriented relative to the existing structure. Then maybe there will be another bundle adjustment to refine the structure that is there and that it fits better to the other images. And so we can make these feature points and camera orientations becoming bigger and bigger and bigger, right? And then there will be some new structure points which has to be initialized and so on. So we can subsequently add new images, recalculating structure and recalculating motion step by step. There is an optional block in here, which we can see here from this green square. It's georeferencing. As I said before, if the final result should be in a global coordinate system, then we need some points, either the cameras or some points in the object space, which have known global coordinates, right? And these can be also included here in this part. Yeah, this is usually then after this is finished and before the final step is done, which runs a final bundle adjustment on the complete image block which has been created here. Yeah, so the output here is a good initial solution for a final bundle adjustments which is operating on the full set of images and object points. And this can include GPS or ground control point information, and then the final result is a sparse point cloud which is georeferenced in the best case. This is the sparse point cloud as an example of it. So each of those points have been detected before in the feature detection step, and has been recognized in other images. There has been correspondences and so on. And because this step so far used very distinct points, which are clearly visible, like corners or things like that, the point cloud here is not so dense, right? And especially in areas where we don't have much structure in the images. So this here is probably you probably can't really see what this is anyway, right? But if we have like surfaces which do not have a lot of contrast, then there will be no points which can be found in one image and in the other image. And then there will be no points later in the result, in the sparse point cloud. And this is why the sparse point cloud is not what we actually want to have as a final result. So there is an extra step now to make this point cloud denser, more dense, and this is called multi-view stereo. So now the goal here is try to find much more correspondences between images than just using features. Yeah. So these features find distinct points, and we now want to have much more correspondences between the images so that we can make our point cloud much denser. In the ideal case, we match every pixel of every image with pixels in other images. Yeah, this would be the ideal case. So that means also that we match areas rather than features. Yeah? So the idea is we have to also match areas where we can't find very distinct features. We can use, so this approach uses usually known orientations, epipolar constraints. So there's much more knowledge behind, like the extrinsics of the camera, for example, are assumed to be known here. So we don't need to estimate them as well in parallel to the object points. We take them as known because they come out of the structure for motion algorithm. Then there are methods. I don't want to go into the details. There are methods called multi-resolution, which can help to make this matching between the images much better. You can use multi-image matching, so not just looking at two images and find the correspondences, but look at multiple images. And you can make assumptions on the surface smoothness. That means as you say, for example, that if the neighboring point is at some point in the object space, then the point itself can't be so far away from it. So this is basically a smoothness assumption on the environment. And these assumptions then can be integrated into the algorithm. And one of these algorithms is called semi-global matching. You may have heard of that as well. The result is a dense cloud. So a dense point cloud of the environment. So, and this is here. This is now the same building that we've seen before, and now we see it looks very, very, more dense, photorealistic, because all these points also have a color from the image, yeah. And here you can see that even the surfaces where there is not much contrast visible here are reconstructed very well and very dense. Yeah. So this is now the result, the measurement result of a UAV flight and the corresponding structure from motion pipeline, which has been processed afterwards. You could spend a lot of time on comparing UAVs and laser scanning and so on. I just wanted to point to a very just give a quick example on the differences. This here is a crop surface. So this is a piece of an agricultural field. It's actually wheat. It's, I think, something like 1 by 2 square meters, right? So this is 2 meters. Maybe I should know that here. So this is roughly 2 meter, and this is 1 meter. And this here is done using a terrestrial laser scanner. So it's a scanning system. And this here is reconstructed using a UAV with a camera and the pipeline that I just described. You can see the difference quite good, because here these white is the image reconstruction, and the other ones, the greenish yellow ones, are from the laser scanner. And you can see that here the UAV the image reconstruction basically smoothes out many of the things that the laser scanner actually measures, right? So the reason for this is that the 3D measurement here, right? So for example, this point is the result of a distance measurement to the scanner, right? So here's a scanner. Oh, what's happening here, right? There's a scanner, and this is the distance. Sorry, I need to somehow remove that. What's happening? Anyway, this point here is a result of a measurement, of a 3D measurement. And this here is a result, these white points are results of the reconstruction process described before. So there is some assumptions on the smoothness of the surface. And a crop field, a wheat crop field, is not smooth at all, right? So there are many, as you can see, there are these ears, there are leaves and everything. So it's a very, very inhomogeneous structure. And this is smoothed out a lot by this reconstruction surface from the images. So this is a very good example that a laser scanned point cloud can resolve much finer structures, assuming that the laser spot size is not too big, right? Than the image-based reconstruction can do. This is a very extreme example, yeah, but it shows that the same surface look very different depending on if I do a laser scan or if I do an image-based reconstruction. Okay. Another important thing, I mentioned it before, is georeferencing. So georeferencing means that what we want at the end, that our point cloud, our representation of the 3D environment, should be in a global reference frame. This is what we call georeferencing. And we do this automatically with a mobile laser scanning by generating our trajectory in a global coordinate system, and then the laser scans are in that, the scan points are in that coordinate system as well. So how do we do that with this image space system? And I explained that quickly already. So if this here represents this this bundle of images which have been taken, and we have here on the ground all these object points which are seen in different images, then the whole structure from motion pipeline creates estimates the position and orientation of the cameras and the position of these object points here. And only if we know some of the points in the object space or some of the coordinates of the camera in a global coordinate system, then we can transform the whole thing into the global system. Or actually not transform it after reconstructing it, but putting these coordinates, putting these known global coordinates like those ones here, or the ones, the camera coordinates here, into the bundle adjustment, and then the result will be a georeferenced, will be in the global coordinate system. Sorry. We have two options to do that. Option one is we use known scene points, yeah, which is the example here, where these triangles here are assumed known positions in the world frame, and then everything is oriented so that it fits to those coordinates, to those points. Yeah, and this is called indirect georeferencing, and this is what's usually done if you do aerial-based imaging. Usually you put ground control points everywhere, and then you can do the indirect georeferencing. Option two is that we use the onboard sensors, like of the drone, to absolutely orient images. It actually even means that we don't do any SFM, right? So it means that we measure the full pose of the camera and then directly using this to reconstruct the 3D environment from the images. Yeah, this is called direct georeferencing, and this is rarely used. It's the only way to do georeferencing if you have a laser scanner on the drone, right? Because then you can't search for these image points. But for image-based georeferencing, usually it's not used. But there is an option 3, which is very often used. It's basically a combination of those two. Yeah. So that means we use known points here on the ground. Yeah, and we also use known coordinates of the camera. Yeah. So if there's a GNSS receiver on the camera, then we get a coordinate from it, and then these are, together with some ground control points, are put to the bundle adjustment, and then everything is georeferenced. And this is called integrated sensor orientation. And this is actually very often used nowadays because nowadays the UAVs and the cameras have GNSS receivers integrated. Okay. I go through the 3 examples and to the 3 options for georeferencing and give some examples. So this is the classical one, the indirect georeferencing. What we do, I said it before, we deploy a set of ground control points and measure their coordinates. Yeah. So this is how they look like. Usually, the main thing is that they are visible in the images, right? So this here is a black and white target, and the middle point is then measured using this pole here, using a GNSS, RTK GNSS, or you can even do it with a total station. Whatever your geodetic equipment provides you, you can measure the 3D coordinate of that point. And then you find those points in the images. So they need to be big enough to be visible in the images. And then you know in every image which has these ground control points visible, you know one point in the image with a global coordinate well defined. And this is the idea. Just as an example, how many of these ground control points are actually needed. This is just an example of some vineyard here, 70 meter wide, and we measured this vineyard like last year, and we put, in this case, we put 6, 7, 8 ground control points. It's good to have them at the border of the area that you wanna measure, right? And then some in the middle. Maybe these wouldn't have been necessary. You can probably spend hours on discussing how many of them are really necessary, and it depends on many things, on the camera, on the flight height, and so on. I don't want to go into this now, but this is just an idea. So if I have some area, I probably need a couple of points, like 6 or 8 points to georeference everything. For the direct georeferencing and for the integrated sensor orientation, for both options, we need to know some information of the camera orientation, which means here position and rotation parameters. Yeah. And we need it at the time when the image was taken. And this is what we need, summarizing what we need a system or an algorithm to determine the position and orientation of the UAV, right? This is what we talked about in the lecture trajectory estimation in the last semester mainly. Then we need the relative orientation, of course, between the UAV and the camera. Yeah, so we need to know how the camera is oriented and where it is actually in the UAV coordinate system. And this has been dealt with in the lecture system calibration. And then we need the exact time when the camera was, when the shutter was released, right? So synchronized, we need the exact time when the image was taken, synchronized with the trajectory estimation. And this was part of the lecture sensor synchronization. So, these are the things that we need if we want to do a direct georeferencing or an integrated sensor orientation. So how can we get the trajectory of a drone? And I give some examples of what navigation sensors are actually available on UAVs, because these are the ones that we need, right? So in our mobile laser scanning example, we had this very heavy, huge and expensive inertial measurement GNSS unit, which does the job for us, right? But we can't put these on UAVs, so there are different options to do that. So standard UAVs, and I consider this like this Phantom 4 from DJI here, or just to name some other company. Actually, what is the name of the company? I think it's Unique. They usually have some low-cost inertial sensors, which are used for the in-flight stability control. So all this controlling the stability of the drone, these internal control loops are done using some low-cost inertial sensors, right? And they can also provide you with an angle, with 3 angles actually, but they're not very accurate. Usually they also have some low-cost code-based GNSS receiver as you know from the GNSS lectures, in the order of several meters of accuracy. And these sensors are used for navigation and mission control, right? So these are originally not used for tagging images, but you can use them for tagging images, right? So this is done in the case of the Phantom 4, for example. So these sensors can also be used for image tagging, and because the orientation, the accuracy of the GNSS is not so good, like it's in the order of several meters, the time synchronization and the calibration is not critical at all in this case, right? So because the accuracy of the drone is only 3 meters, the lever arm between the drone and the camera is just negligible. And the same is for the time synchronization. If we don't know exactly the time when the image has been taken, we have a few, like 1 or 2 meters error due to the time synchronization, which is not a problem in this case. So if you want to have a precise georeferencing, so if you can use those coordinates here, you can use it to georeference the point cloud with a structure for motion, but the result can be 2 or 1 or 3 meters off the real object, right? So if you want to do it precise now, you need an indirect georeferencing. So that means you need some ground control points to refine the absolute orientation or the absolute position of the result. Nowadays, there are more and more commercial solutions who add an RTK GNSS receiver to the drone. Yeah? So one of the first who did that commercially was this UAV here. It's actually a small plane from Mavinci, from a company called Mavinci, and they have an RTK GNSS receiver on the drone. So we can do we can use the coordinates of the of this RTK GNSS receiver when they are taken when we know them when the image has been taken. We can use this for georeferencing the whole point cloud. Of course, if you want to do that in real time, you need some sort of correction data, and you need to transmit the correction data to the drone. But usually, this is not needed in real time, so you can do that offline, right? In this case here, there is a master station on the ground. It is recording all the data of the master station. This plane is recording all the data, all the observations from the receiver here, from the rover, and then later on there is some differential GNSS RTK processing going on, and then we have the coordinates of the plane. Now, since this coordinate of the plane is accurate within 1 to 3 centimeters, the time synchronization and the calibration becomes very critical, right? And this is the reason. Because this is in the same order of magnitude or even larger, right? So the lever arm between drone and camera is probably 10 or 20 centimeters, and the times and the accuracy of the RTK is 1 or 2. So it's very important to have the time sync and the calibration well done. And this is the reason why most of these commercial solutions only work with certain cameras. So you can't just put any camera there, because you have to make sure that the lever arm is well known and that the time synchronization works as you want. Mostly, just another information, mostly RTK GNSS is used only for image tagging and not for navigation, right? So the reason for this is probably that the RTK GNSS can be prone to errors and jumps more than the actual code-based solutions. So you don't want to rely on this. You don't want to rely on this to navigate your drone. So mostly they are only used for tagging, and for the navigation, there is an extra GNSS receiver who's just doing the navigation part. So these high precision image coordinates then can be integrated in the bundle adjustment, as we said before. And this is then called integrated sensor orientation. So these, if you do this and you use the high accuracy GNSS, then your resulting point cloud is already georeferenced within a few centimeters. There are also UAVs which have high-end IMU GNSS receivers, And these high-end geodesy are usually used for direct georeferencing of laser scans. So this example here is a laser scan. It's a profile laser scanner, which is, as you can see here, it's attached to a UAV, and then we use this IMU here. In this case, it's an IPX20 from a Planix to georeference the laser scan. So this here is the same principle as we talked about already a few times in the case of mobile laser scanning. It's just that the vehicle now is just a UAV and not a car, right? So this is the same thing, and this is then what we call direct georeferencing. The pose is directly used to globally orient the scans. Okay, let's summarize for now how we derive point clouds from images using the so-called SFM pipeline. So we generate overlapping images with UAV. So we haven't talked about how these images, how much they have to overlap. This is just some general overview. So the important thing is that they have overlap. Otherwise, we wouldn't be able to find features in multiple images, because this is a major thing here, right? So we then find features in the image, and then there is a matching between the features, as we said before. Okay, so we have the same points in multiple images that we can find, and we can find correspondences between them. All these correspondences, these corresponding points, go then into the bundle adjustment, which then generates the camera calibration parameters. That's one thing, and it generates the position and orientation of all of the images, and the position and orientation of the feature points in the object space, which correspond to the points that we have found in the image. If we also put georeferencing data in here, then the result, the sparse cloud result, is already georeferenced in the proper world coordinate system. This georeferencing, as we said before, could be either done by knowing the positions of the cameras before with a GNSS device, or knowing some coordinates in the object space by, for example, using ground control points. The next step is we have this sparse cloud is then to generate a dense cloud using multi-view stereo, and this was mentioned only, this was explained only quickly, but the idea is to find many correspondences between different images which are much denser than those here, and which match actual features, areas in one image to areas in the other image, and so we can generate a very dense cloud, and this is then the final result of the structure for motion pipeline. Afterwards, which is mentioned, I haven't talked about that at all, but usually this point cloud can then be used to generate digital surface models or orthomosaics, which are often used. Which, yeah, we will not go into details for this. Okay, so this is now the procedure how to generate a 3D point cloud using images. I now want to provide some examples, some project examples, which we were involved in with our group, and which just show you what we've done in our research and where we used all these methods that I showed before. Sorry, I forgot to mention, there's many software available which can do the job, right? We usually use, in our group, we use Argisoft Metashape or Pix4D, which are commercial solutions. There are many free solutions as well. I can't really say which of them is good and which of them is not so good. I have no idea, to be honest. This is so not tested or no ranking, whatever. It's just a list. And if you're interested, you don't have to pay money to try the things. And if you Google, you will even find more of those free software packages. Okay, sorry, I forgot that. So now we come to the project examples that I wanted to mention. The first project example is a DFG research group, which is called Mapping on Demand. So a DFG research group was started in 2012 and finished in 2019, and it involved many groups. I would show you who was involved. And the idea was to generate 3D reconstruction of objects and environments using a lightweight unmanned aerial vehicle. And since this year is pretty normal nowadays, we back then had some ideas which are not so normal. So we wanted to make it based on a semantic user request, like, for example, find all open windows, right? We want to have no preparation of the environment, so we didn't want to put any ground control points anywhere. We wanted to have a result in real time or close to real time, so no offline processing needed. And we want to have the flight fully autonomous, so trajectory planning, collision avoidance, and everything else. And we want to have interpretation of the results, so like find all open windows needs some sort of interpretation of the results. So what is a window and what is not a window? Yeah. So this was the idea of that research group, and I will and it involved a few like parts, like the real-time pose determination. This is the one I will talk now about, because this was our job basically. Incremental mapping and exploration was by the photogrammetry group, and then there were groups like local perception and obstacle detection from the Uni Bonn computer science department, 3D surface reconstruction from Munich. Computer graphics department was responsible for generation representation of 3D and 4D maps, and there was something about semantic building models because we wanted to interpret the results. I will focus on these two parts here because this is the part where we were involved in. So we build a custom unmanned aerial vehicle. For this, the main reason was that when this project started, companies like DJI didn't exist. So it was not possible to buy a reliable and working base platform, which then could be just extended by your own sensors. So we had to basically build up our own UAV to be able to put all the stuff on it that we wanted to have, right? And we didn't need to start from scratch because there are like frame sets and things like that available, but we customly designed the final setup. What we had here on the UAV was a dual frequency GNSS antenna, this one here. We had a single frequency GNSS antenna, this one. Then there were stereo cameras at the front, pointing to the front and to the back, here and here. And there were fisheye cameras, so to see a lot of the environment. And then we had a direct georeferencing system. I will explain later what that is. So that is a GMSS IMU unit mainly, which was here, which was responsible to generate position orientation of the whole thing in real time. And then there is a camera here, which was used to reconstruct the environment. This was the actual measurement sensor here. So it was an industrial camera with 5 megapixels. Okay. This georeference system, I said, is also custom design, which we developed in our group, and it's basically a GPS IMU unit, which with a low-cost IMU, so not so expensive as the big one. It has a GNSS receiver here, right, and there is some IMU is this one here. It's an accelerometer, ankle sensor, magnetometers in there, barometer, dual frequency GNSS receiver, single frequency. That's what I said already. Then there's a radio link for GPS correction data. So because we wanted to have a precise position in real time, we of course need to have the correction data from some master station, right? So you need to have that link available. And there is some input for external sensors like the stereo cameras. So, and this is also important. If you want to integrate this, you have to make sure that it's time synchronized with all the other stuff. And we developed this because back then similar things were not available, and it was and we wanted to have the full control of the system with respect to all the connections, interfaces, and the software. We developed orientation algorithms, position orientation algorithms using Kalman filters, and this was pretty much similar as you learned in the first semester of that course. And we were able to derive accuracy and sub-degree, centimeter accuracy and sub-degree accuracy for the orientation. Just to repeat what we developed in terms of algorithms, we basically did a strap-down integration, like we used to simplified inertial navigation algorithms. All of this you learned in this first semester, but we ignored the Earth rate and the transport rate here. So we simplified it a bit, and we used this to calculate position and orientation over time. And then we used as a measurement model, we used a GNSS observation. Yeah, okay. So here the observation model was the measurement of the GNSS was the measurement of the current state of the drone, like current position of the drone, and then corrected by some lever arm, which is the vector here, because the GNSS antenna was not exactly in the middle of the drone which was considered as a reference point for the position of the drone, right? So this lever arm needed to be considered, and of course then the orientation, which is here, the current orientation of the system, plays a role, of course. Next measure model was the Earth's magnetic field. So we used the Earth's magnetic field as well as a sensor, and this gives us, of course, some sense of an absolute orientation of the drone. I don't go into details here, just you can look up again how this estimation worked, and then this is just to tell you what measurements we actually used here in addition to the strap-down inertial navigation. And the last measurement was a local GNSS baseline, because we had two receivers on the drone, right? This, and we could measure the baseline vector here, and this gives us also a measurement of the absolute orientation of the drone. You might ask now, why do we need this? We have a magnetic field sensor, but to be honest, magnetic field sensors is something that you should not use on a drone. That's what we learned. It's not a big surprise actually, but if you have magnetic field sensors, are usually strongly disturbed by the currents that are going here through the engines and by all the metal and everything. So it's good to have an alternative, and the only alternative, or not the only, but the next alternative to using magnetic field sensors to get an absolute orientation is a GNSS baseline vector, which we have here. Okay, what we then did is we tested our algorithm that we calculated on board in real time, and we tested the accuracy by comparing it with an offline bundle adjustment. So we used the bundle adjustment that we talked already before to generate position and orientation of the cameras, and we then calculated this position and orientation which comes from the bundle adjustment with the position and orientation that we derived in real time on board. And here you can see the differences in the position. Yeah, so east, north, and up. So we can see that its standard deviation is in the order of 1 or 2 centimeters. So this is pretty much what we expect from a real-time kinematic GNSS. Yeah, it's always below 5 centimeters, and in the orders of a few centimeters. And the orientation here is the orientation differences, the yaw, pitch, and roll differences. And you can also see that the yaw is a bit critical. Here, for example, it's drifting a little bit, and the pitch is a bit more stable. But it's all in the area of something below a degree, which we are able to generate here in real time on board. Okay, this is another accuracy analysis, but with the same principle. We have here an agricultural field. We have measured ground control points here, and then we did a flight. You can see the flight pattern here, and each of those points is one image taken from the scene, and then we used the bundle adjustment to calculate the positions of all these images, all the cameras, and we compared this with the real-time calculated cameras on board, the camera positions on board. And again, we see that it is in the order of a few centimeters. We can also see some interesting thing, which outside of this area here, the difference becomes bigger, right? So the differences between the photogrammetric solution of the camera position and the onboard camera position is becoming up to 4, 5, 6 centimeters. And we can clearly say that this is due to the fact that outside of the area of ground control points, the bundle adjustment doesn't work well anymore. So there's a bowl effect or something. So that means that in this area, the differences, the errors, very likely come not from the onboard calculation, but from the bundle adjustment. Another thing that we did in that project was we integrated those onboard calculated positions and orientations with the data from the stereo camera systems in order to improve the trajectory estimation. Without going into details here, the bundle adjustment, the stereo camera used an incremental bundle adjustment to reconstruct the trajectory, right? It also, as described before, it used feature points, corresponding features, and so on, and then it was able to calculate the trajectory here by always refining points and calculating the motion here. So this is actually similar than the structure from motion that has been described in the beginning. And what we did, we integrated those information with the information from the GNSS. And we even did that in a tightly coupled way. That means that we combined this relative motions that come from the camera with the raw observations from the GNSS. So with the double differences that we took, with the double differences that we got from the receiver. So we could integrate this to one single stable trajectory estimation. We did some test flight just to show some results here. So this here was now 4 different flights in the area here of that building and that trees. It's an area called Frankfurt, which belongs to the uni, and it was a 5-minute flight each. And it was manual control, so no automated flying here. And what we did, we then used our onboard georeferencing system to tag the images, right? So we used the real-time generated position orientation and assigned them to the images that have been taken during that flights. And then we used the images and the position orientation data to create a dense point, a sparse point cloud, the first thing, and then use dense image matching as a free software which does the dense cloud, and then we get a georeferenced point cloud. And this is what it looks like. So we have those. This is a point cloud as a result from that software pipeline. Each of the points has a global coordinate, and that was the result back then. This is a building. This is this building where we flew, and this is a point cloud. And here you could even see, if you look a bit closer, this window here is open, right? So this would be now a basis for, so according to the idea of the project in the beginning that I said in the beginning, we could now detect this window here as open because the plane here in that window is not vertical, for example. Good. Okay. So this was just an example of one research project that we did here together with Cheryl Stachner's group and some other groups. And there's another thing, another project. Oh no, sorry. One final plot. I'm sorry. So this is just an accuracy analysis. So we compared the results of the reconstructed point cloud with a terrestrial laser scan, which has been georeferenced using ground control points, which we take as a reference, and we compared it, and it was basically all below 10 centimeters accurate. It's a bit difficult to say, but this just gives an idea how accurate this is. So this here, the red ones, is actually the sparse point cloud. It's not the dense point cloud. And we computed the difference between the sparse point cloud, the reconstructed one, with the terrestrial laser scan point cloud. Okay, another project, completely different, but using also UAVs and images and 3D reconstructed point clouds, is the project CropWatch. And in this project, the goal is to observe plant parameters like the canopy height, for example, from UAV flights during the growing seasons. Right. So it's one might be interested in how a plant actually grows during the season, possibly to interact or to do fertilizing or weeding and all these kind of things. So get a proper status of the field from flights with a UAV. So the first thing is then creating georeference point clouds, right? So we have this, we have the drone, we fly over the field, do this flight pattern, have many images with overlap, and then create a 3D representation of the field, which is georeferenced. And if we do that multiple times, and because it's georeferenced, we can then put them basically together. So we first extract the ground reference. So because if we want to calculate the plant height, we need to have the difference between the tip of the plant and the ground. So what we need first is the ground, right? So we first get the ground from some flight where there haven't been no plants, and then each time, every 1 or 2 weeks, we fly again and create a 3D point cloud, and then we calculate the difference between this, and this gives us the plant height. If we do that, we can then have like we can generate raster data. So this, for example, is like rasterizing these plant height information, and then we can generate maps like this. This is a height raster in week 1, 3, 5, and 6, and this is the height of the plant in centimeters. So we can see that some of the plants are really growing higher than others, and there are some holes in here, and you can even see here the 5 points. The 5 round things here are where the ground control points have been, and we removed all the plants around the ground control points so that we can actually see them. And this is why here at these points you don't see the height is still 0, because we removed the plants. And these lines are the lines where the tractor has driven in order to manage the field or spray the field and do all these things. You can then analyze those time series of height for different genotypes. It's just like a result plot that the plant scientists, the agriculture scientists are interested in, right? You can see a genotype which has been managed with 2 different management systems, one with a lot of fertilizer and the other one with not so much fertilizer, and then you can see that this one is growing faster than the other one, for example. And this difference is very big for this genotype, and this distance is not so big for, let's say, this genotype. So this is just to show you what you can do with those information. So other application areas, of course, are the building industry. Like you can do progress documentation, change detection. You can fly every day and can see what happens where, which holes has been dig, what happened on the construction side. You can use it for general surveying and mapping, finding buildings, roof catasta, and all these things are possible, of course, with drones. This may not be a surprise for you. This has been already a while in the normal kind of portfolio of measurement of surveying offices. This is something that we did together with some geomorphologists. The idea was to measure how this piece of soil here is moving. It's called the soil deflection loop, and it's moving slowly towards the so downwards. And we used a drone and a camera and to fly 1 year and then the next year, and then we try to calculate the differences in order to find out how fast it's actually moving. And it's just to show how good, how nice these point clouds actually look like. So these are the stones here, these stones, and you can really reconstruct them very well using the images. Yeah, this is another example. This is an example of the Beethovenhalle here in Bonn, which has been it's still in a big construction, actually in a renovation or rebuilding, and before that it was completely measured in 3D using a drone by this company. It actually was fused. I think it was fused with laser scanners as well. But this is just an example. So yeah, this is what you can do, of course, what you can do with it. Okay, so to summarize what you've learned today, so we talked about how can point clouds be created from images. We talked about it more on a rough concept kind of thing, not so much into the mathematical details. So what are the processing steps in an SFM processing pipeline? This is what we said as well. And another important thing, what georeferencing options are there for UAV-based mobile mapping? So how can you make sure that your result, your product at the end, your point cloud is properly georeferenced? And also, the question is, how can you calculate the poses of an UAV? This was described a little bit in that example from the Mapping on Demand project. And what are applications for UAV-based mapping? So these are the things that you should have learned today. And with this, I want to thank you. Yeah.